Hi, I'm Viraj Prabhu, and I'll be presenting our work on SENTRY, Selective Entropy Optimization via Committee Consistency for Unsupervised Domain Adaptation. This is joint work with Shivam Khare, Diksha Karthik, and Judy Hoffman. Adapting deep models to new domains is an important problem, as it is impractical to label a new large dataset for every deployment. Ideally, we would like to be able to adapt models trained on labeled data from a source domain to a related but unlabeled target domain. This has been extensively studied in prior work as unsupervised domain adaptation. However, most modern unsupervised DA methods offer limited success in the presence of additional cross-domain task label distribution shift. This is because they rely on distribution matching between source and target distributions in a shared representation space, which has been shown to implicitly assume similar label distributions across domains and can lead to incorrect matching otherwise. This limits their utility, as in practice, while we may be able to curate source label distributions, we have no control over the target dataset. Recent work based on self-training has shown promise for adapting under additional label distribution shift. Broadly speaking, self-training methods either perform supervised training on model predictions on unlabeled data or minimize conditional entropy to encourage confident predictions. Unlike distribution matching, they do not make assumptions about label distributions. However, unconstrained self-training for DA can lead to error accumulation. Consider a toy 2-class example where solid pink and hollow blue denote labeled source and unlabeled target instances respectively. Under a domain shift, some target instances are initially misaligned, and entropy minimization on these will increase model confidence, thus reinforcing model errors. To address this, we propose selective entropy optimization, or SENTRY for short. For the same toy example as before, we first identify reliable target instances on which to self-train. Prior work has used model confidence for this purpose, but under distribution shift, confidence is known to be miscalibrated. We instead estimate reliability for an instance by generating a random set of label-preserving image transformations and measure the predictive consistency of the model across this set. We then increase model confidence on highly consistent instances and reduce it on highly inconsistent ones, leading to robust domain alignment. The complete SENTRY algorithm is as follows. We first sample a labeled source and unlabeled target example with class balancing using true and predicted labels respectively. For the target image, we apply a committee of randomly selected label-preserving data augmentations. We then obtain model predictions on the original as well as augmented target instances and measure their consistency. We first mark target instances for which the model's predictions on a majority of augmented versions and the original version are the same as consistent, and minimize predictive entropy to increase model confidence. Similarly, we mark instances on which the model's prediction on a majority of augmented versions and the original version is not the same as inconsistent, and maximize predictive entropy to reduce confidence. We optimize this SENTRY loss in conjunction with a supervised source cross entropy and a target information entropy loss proposed in prior work. We present results on 31 domain shifts from 5 adaptation benchmarks for image classification, including datasets with natural cross-domain label distribution shift, as well as custom shifts specifically designed to stress test adaptation under LDS. Here are our results averaged over 12 shifts from a 40-class version of the domain net benchmark. We measure transfer performance on the target test set and note that a model trained on the source domain without any adaptation achieves 66.8% average accuracy. As baselines, we first include methods based on distribution matching and a method designed to overcome only label shift. We observe that these achieve small or no improvements over the source model. Next, we present results for recent methods designed to overcome joint data and label distribution shift based on relaxed distribution matching, on confidence-based self-training, and self-training combined with contrastive and mix-up losses. We find that the self-training based methods achieve larger improvements over prior work. Finally, we present SENTRY, which achieves a 3.6% absolute improvement over the next best method. SENTRY also achieves significant improvements upon prior work on other benchmarks, on a label distribution shifted version of the Office Home dataset, on standard Office Home, and on WISDA. Altogether, SENTRY sets a new state of the art on 27 out of 31 shifts that we study and is competitive on the others. Finally, in our paper, we performed several experiments to analyze the behavior of our method. We find that SENTRY leads to performance improvements across categories, aligns an increasing amount of target data over the course of adaptation, and is highly precise at identifying reliable and unreliable target instances. Thank you for listening. For more details, please visit our project page.